there we go. All right, recording. All right, so we're recording. Do you have your approved calculator, specifically the one that you're going to be using on the exam? I had the unfortunate event during my last 1250 exam. The last like 10 minutes, a student asked me, they didn't know how to use an exponent on their calculator. They showed me their calculator and they're like, how do I do exponent 3? And there's only like 10 minutes left and I couldn't help them, but like, you know, you don't want to be put in that position. So do make sure the calculator you use at the exam is the one that you, are using to practice, so you can understand where all of those buttons are, because we're doing a lot of different kinds of calculations using natural logs, undoing natural logs, power to the 14th, undoing a power to the 14th. So do understand how to do that. And then finally, do you have the supplemental information packet? I posted that for my students, but hopefully you have access to that too, so you know exactly what equations you will get at the exam. All right, so we will get started here. Any questions? So I'm recording. Okay, we'll just go. All right, what chapter do we want to start on? 17. Okay. We're just gonna go in order. I'll get to 20, I promise. So if you don't see here at the top of the packet, midterm 3 covers the last part of chapter 17. So this is specifically titration curves, KSP and KF, K formation. So the new types of equilibrium that we studied. Chapter 19 is chemical thermodynamics. So we introduced the idea of entropy. And then chapter 20 is electrochem. All right, so let's just do a little bit of chapter 17 review. So these questions, are these specific salts, acidic, basic, or neutral, technically was assessed on midterm 2, but these ideas are still important. They come up again in midterm 3, that these topics don't go away. So let's predict whether these salts, or actually they're not all salts, they're just random things. So if I put this in water, what will the pH be? Basic, acidic, or neutral? So let's see if we can't identify it. So NH3, what is that? You put it in water, the water becomes basic. Yes, it is a base. Oftentimes when I think about bases, we think about Kb. When we calculate the pH of just a base, it's typically x squared over its concentration, where x equals Kb, where X is equal to hydroxide concentration. So that's a little bit of a review for chapter, or for midterm 2. Oftentimes, we give you a Kb for a base. Oftentimes I will just call it B for base. Yeah, all right. The next thing, NH4NO3, what the heck is that? Well, first, NH3 is neutral. NH4NO3 is a little bit different, where if you put that in water, it breaks up because it's an ionic salt. So if we named this would be ammonium nitrate, all right? That's back in Chem 1210, right? 1210, you remember naming ammonium nitrate. So this is a strong electrolyte. It dissolves in water and becomes NH4 and NO3 minus. So now we can inspect those things separately. All right, so ammonia was just one thing that goes into water, it's a base. But these two things we need to consider separately and think, okay, what are those ions, either acidic, basic, or neutral? So what we're looking at here with these ionic things, we're looking at the conjugate, either acid or base forms of their neutral species. So NH4 plus is actually the conjugate acid of NH3. So therefore, NH4 plus is what? Acidic, basic, or neutral? Acidic, yes, acidic. Nitrate, on the other hand, is one of our neutral salts because it's the conjugate of nitric acid, which is a strong acid. So what we're looking for are either weak acids or bases, but we're looking at their conjugate form. So this is a neutral salt, the nitrate component. So if we had something that's acidic and neutral overall, if you put ammonium nitrate in water, it's going to be acidic because of the nitrate that is, or sorry, not the nitrate, because of the ammonium that is there. All right, okay. HBr, what is that? That's a strong acid, yes, strong acid. All right, so hopefully you're thinking about how you would calculate the pH of these things. This is a strong acid, great. NaCl, what is that? That is a neutral salt, yes. When I say a neutral salt, that means if you put sodium chloride in water, the pH of that water will be 7, yes, so it's pH 7. Caveat, assuming we're at what temperature? 25 degrees, yeah, so neutral water is only pH 7 at 25 degrees, only at 25 degrees. Okay, calcium hydroxide, what's that? That's a base, yes, or basic, whatever. All right, the next thing. This is another salt, so separating it into its components here, we have K plus and CH3COO minus. Yeah, this is going to be basic because that CH3COO minus is actually acetate. Acetate is the conjugate base of acetic acid. Acetic acid is an acid, so therefore acetate will be a weak base. Great. K plus, does K plus contribute anything to the pH? No, it's neutral because KOH is a strong base, so it's a neutral salt. All right. Then this next substance, this is acetic acid. All right. This is acetic acid, the neutral acid, so this is acidic. Acidic. Right. Ki. What do we think? So that's another salt. Just try to name it. If you name it and you have to use ionic naming rules, then it's a salt. So this Ki is composed of K plus and I minus. So let's look at those individually. We already said K plus is pH neutral, but what about I minus? What about I minus? Also neutral, yes. Did you just memorize that? Kind of, sort of. We know I minus is pH neutral because it's the conjugate of one of the strong acids, HI. So let's just do this last one and we'll go through all the strong acids. Calcium fluoride. What is that? Acidic, basic, neutral? So we have calcium 2 plus, F minus. This is going to be basic because F minus is a weak base because HF is a weak acid. Okay, great. So let's just quickly go through all of the the strong acids, all right? We had you memorize these in Chem 1210, the strong acids. I just kind of use the periodic table to help me. The binary acids, HCl, HBr, and HI. Those are all strong acids. The other ones will be nitric acid, so HNO3. The next one is H2SO4. And then we have some chlorine-containing oxo acids, HClO3, which is chloric acid, and HClO4, perchloric acid. So that means all of these things, if we had a 0.10 molarity of all of those things, we could calculate the pH, right, of those, and it would be the exact same calculation. It would just be pH equals negative log 0.10 molarity, because all of those substances completely donate one H plus into water. They completely dissociate. And whether you have 0.1 molarity, HCl, HBr, HI, all of them will have the same pH. And if you calculate that, what is that? Is that pH 1? pH 1? Yeah, all of the, if it's a strong acid, they'll all have the same pH. So, and I think that's what this like kind of next idea is. Okay, we identified A through I as either acidic, basic, or neutral. Let's pretend if all of these solutions were 0.1 molarity, how would we go about calculating the pH, assuming Kas and Kbs are given? So let's just go back through these and think, okay, if we have 0.100 molarity NH3, how would we calculate the pH? We would use the Kb that is given. We would set that equal to x squared over 0.1 molarity, where x squared in this case is concentration of hydroxide. Kb would be given to you. All right. And how I got this, expression Kb equals x squared over 0.1 molarity, that's just from the ICE table with an approximation in there. All right, so we've done a lot of those already, so I hope that you can kind of think about the ICE table. All right, the next substance, what if we had ammonium nitrate, and that was 0.1 molarity of ammonium? How would you calculate the pH of that? Can you use a Kb expression to calculate the pH of ammonium? No, because ammonium's an acid, so you have to use Ka. But will the question give you Ka of ammonium? No, they're going to give you what? Kb of ammonia. But that's okay, because Ka and Kb are related to one another. Ka is equal to Kw over the Kb that's given, and then that is equal to x squared over whatever, 1.1 molarity. Oops, x squared. But in this example, when you calculate for x, x is the concentration of what? H plus, yes, x is equal to the concentration of H plus, because you used Ka. All right, next one. HBr. If you have 0.1 molarity of HBr, what is the pH? It's 1. It's just 1, because we just put this concentration into the pH calculation. Equals negative log 0.1, so it's equal to pH of 1.0. It's a strong acid. Okay. What about NaCl? It's just 7. Yes, because it's a neutral salt. Doesn't matter what concentration it is. All right, calcium hydroxide. If you have a 0.1 molarity calcium hydroxide, how are you going to calculate the pH of that? Calcium hydroxide, what kind of base is it? Strong base, yeah. So we just need to figure out what's the concentration of hydroxide. So what's the concentration of hydroxide present? Is it 1 molar or 0.1 molarity? No. What's the tricky thing? There's 2 hydroxides, so it's 0.2 molarity. And then that's the number that goes into your pOH calculation and then your pH calculation. Great, all right. What about the next one? Potassium acetate. You have 0.1 molarity of that. So again, think about how we defined this. Potassium acetate is a what? A base. So that means we have to use what expression? Kb. Kb, but will we be given Kb of acetate? No, we will probably be given Ka of acetic acid. So we have to do the Kw over Ka business in order to get Ka or Kb, and that is equal to x squared over 0.1 molarity. And then when you calculate for x, x is the concentration of what? OH minus, because you used Kb, right? All of this is review. All right, it's review, but like kind of not review, because we would have in midterm 2 just asked you like the pH of like any one of these things. But the thing is, what a titration curve is we're making these species. At the beginning of a titration, we might start with acetic acid, but at the equivalence point, we have its conjugate base. So as long as you're good with these calculations, applying it to titration curves is just a small half step, relating, okay, what species is predominant at these different places on the titration curve. All right, next one, acetic acid. How would you calculate the pH of that? It's an acid, so you use Ka. Will you be given Ka of acetic acid? Yes, you will. So it's just Ka equals x squared over 0.1, and then you solve for x, and x is the concentration of H plus, because you used Ka. All right, what if you have 0.1 molarity of Ki? What is the pH? It's neutral, yeah, so it's pH 7. All right, last one here. This one's a little bit tricky. If we have calcium fluoride, we already said that this is a base because fluoride is basic. So if we have 0.1 molarity of calcium fluoride, we actually have 0.2 molarity of F minus. So F minus is a base, so we use the Kb expression. we do x squared over 0.2 molarity where we solve for x, and that is equal to OH minus concentration because we used KB. Oh, and one last thing, KB here is equal to, I skipped a step. You won't be given KB of F minus, you'll actually be given Ka. So you just have to do a quick conversion using Kw to get Kb. All right, so that is basically half of midterm 2, all summarized. So hopefully you can recognize and not take too much time and recognize how to do a pH calculation for any one of these things. Because on a titration curve, any of those things might be present. So if you can identify where you are on a titration curve, what species is present, you will know what pH calculation to do. So the last piece of the last thing that I didn't include in this kind of review for chapter 17 was buffers. So on a titration curve, there's a couple things to understand what we're looking at. So let's draw a generic titration curve of a strong acid being titrated with sodium hydroxide. So the pH is going to start acidic and then kind of go more basic. So if we kind of label these regions, this vertical inflection, this is our equivalence point. This is the point where your moles of HCl is equal to your moles of sodium hydroxide. All right, so if you did a BCA table and your moles of HCl and moles of NaOH are equal to one another, what you'll see is all you have present is NaCl aqueous. We already answered this question. What is the pH of NaCl aqueous? 7, yeah, so on this titration curve, the pH will be 7 at the equivalence point, but only for this titration curve, because it's a strong acid, strong base titration. So we can kind of reference ourselves to that. NaCl, the equivalence point is 7. Anywhere past, if we add any additional sodium hydroxide after the equivalence point, you've added base. The pH is going to become basic, all right? So any excess sodium hydroxide is going to go into your pH calculation. So you have to figure out, okay, how much of your HCl did you start with? How much of it reacted to consume some of your sodium hydroxide? You need to figure out how much sodium hydroxide is left over, calculate its concentration to get the POH and then the pH. Anywhere before this point, HCl is actually the limiting reactant. So if we kind of go back, let's start at the beginning of the titration right here. Before you even start your titration, right? We have HCl in this Erlenmeyer flask. You got your beaker. Didn't you guys do a ton of these in lab? Yeah, okay. Hopefully this looks familiar. Okay, you put your pH meter in there, into the HCl solution. What's the pH meter gonna read? What kind of pH? It's gonna be acidic, yes. So right here, right where I'm starring, right there. That point, that's at 0 milliliters of sodium hydroxide, meaning that the only thing in your flask is HCl. So whatever concentration that HCl is going to dictate your pH. So this is only HCl. That is a, put the molarity into the pH calculation. Where things can get difficult is any one of the points between the beginning of the titration and the equivalence point. Any one of these points, you're actually just partially neutralizing your HCl. So you actually have to do a BCA table. Actually, I would say that every single point on this titration curve, you need to do a BCA table to figure out what is in excess to calculate your pH. And actually, I drew this this curve a little bit incorrectly. So how I've drawn it here, it looks like there's a buffer region. Doesn't it kind of look like there's a buffer region right here? Kind of looks like that. But the thing is, can you ever make a buffer out of a strong acid and strong base? No, you can't. So I drew this titration curve wrong. The shape should look more like, that, something like that. No, so no buffer region. It's basically like acidic, 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 boom, basic. That's hopefully what you saw in lab. Did you see that in lab? Yes, okay, perfect. All right, so it's look something like that. Okay, oh, someone emailed me about the review session. That's too bad. Okay. All right, so let's not actually do the calculations, but let's just think through how we would calculate the pH of these things. So I've kind of changed it a little bit. I'm gonna put sodium hydroxide in the flask this time, and I'm gonna titrate with an acid. But it's no different, all right? We're just going through the titration curve backwards, all right? So at point A, what's the only thing in your beaker? Just sodium hydroxide. So if you want to calculate the pH, all we care about is that, all right? So we would just calculate POH is equal to negative log 0.1 molarity. We would get something like the POH is equal to 1. So therefore your pH is equal to 13.0, whatever. All right. Sodium hydroxide is the only thing there. That's the easy one. You probably won't get that on the exam, but I just want to reference ourselves. Okay, so we start with 50 milliliters of sodium hydroxide. So let me just calculate the millimole amount of that. That's about, 5 millimoles of base, sodium hydroxide. That's how much is in this flask, 5 millimoles. All right, so let's look at point B. We still have 5 millimoles reacting, but now it's reacting with acid, HCl. So what's going to happen is that acid's going to neutralize some of the base, just some of it, right? Neutralize some of it. Let's use our intuition, all right? If we start with base and we add acid, the pH should go where? Down. It should become more acidic. We're going to consume some of that hydroxide. We need to figure out how much we consume. So what kind of table do we have to use? A BCA table. But you can do a lazy one because titrations, it's always like a 1-to-1 ratio. So you don't have to really do a full-fledged one. You can just recognize that 5 millimoles of base is reacting with how many millimoles of acid? 10 milliliters times 0.1 molarity. Oh, these don't have M's on them, sorry. 1 millimole of HCl. All right, so if these two things react, 5 millimoles of NaOH, 1 millimole of HCl, which one's limiting? I hope you can see, without building the BCA table, recognize which one's gonna run out first, the acid or the base. The acid. So if those two things react, what is left over and how much of it? We have 4 millimoles of NaOH left over. Great. Do I put 4 into my POH calculation? No, that's a millimole amount. I need to put a molarity. So to get molarity of sodium hydroxide, I need to divide that millimole amount by the total volume. Yeah, so what's the, 60 milliliters. So 60 milliliters, that's the total volume. And then that will give you the concentration of sodium hydroxide. And then that will give you, the pH. Do I have it? Something like that. So I get 0.066 molarity hydroxide, then we can stick that into the POH calculation, so 1.18, and so we get the pH is 12.82. Was our intuition correct? We added acid, the pH went down, yay. Because if it didn't and it went up, hopefully something in your brain would think that something's wrong, yes. Okay, so there's B. Let's look at C. What is interesting about C? Can you recognize what point you're at in C? So if you just quick calculate millimole amounts, you have 5 millimoles of sodium hydroxide and you have 5 millimoles of HCl. That's the equivalence point. So that means you just have NaCl present, so your pH is 7. All right, what about D? Again, calculating millimole amounts and looking at the BCA table is going to help you. So in point D, we have 5 millimoles of sodium hydroxide. And then how many millimoles of HCl? 6 millimoles. So this one's a little bit different. Hopefully without writing out the BCA table, which substance is limiting now? The base. So if these two things react, what's left over and how much? 1 millimole of HCl. So does that mean my solution is going to be basic, neutral, or acidic? It's going to be acidic. This is after the equivalence point when we started with a base. So we just need to actually get the concentration, take the mole amount and just divide by the milliliter amount. So divided by 110 milliliters, that will give you some amount and you'll calculate pH. All right, so D is your excess after the equivalence point. After the equivalence point. Good? All right, that's strong acid, strong base. Did you do all these calculations in lab? Okay, all right. All right, well, let's just finish this for fun. Okay, let's draw a generic titration curve of a weak acid with sodium hydroxide. What does that look like? It's going to look very similar to the previous one, except now you actually have to draw a buffer region. So how I know the difference between a strong acid, strong base titration and a weak acid, strong base titration is the very beginning of the titration curve. See how I had to change my titration curve here, where the beginning didn't have a swoosh in it, right? See how it's just kind of like flat and gradually goes up? In a weak acid titration curve, there's always a swoosh at the beginning, and then the buffer region, and then the equivalence point. Okay, that one's pretty intense, but whatever. All right, so here is a weak acid. You're starting with a weak acid, so in this case, HA. There's always a swoosh at the beginning, and then you have your buffer region. Buffer region, and then your equivalence point is still the same. All right, so at the beginning of your titration, you just have HA. If you know what acid it is, you can use the Ka expression, Ka equals x squared over whatever concentration it is to get the pH. But at the equivalence point, what substance is present? Is it Ka or is it HA anymore? No, it is actually A minus is present at your equivalence point, or really technically NaA, right? So the salt form of your acid. And we already went over this. NaA is what? It's a base. It's a weak base. Yes, it's a weak base. And so if it's a weak base, we're going to use Kb. And that equals Kw over Ka, and that is equal to x squared over whatever concentration it is. Do take into account dilutions. So that's how I like to think. These parts of our titration are a little bit different, but just recognizing what substance is present. We have our acid, in this case a weak acid at the beginning of the titration. At the equivalence point, we have the base form of the weak base. And then between those points are a little bit different. So between these 2 points, we actually have the buffer region. So if we have a buffer present, we still have to do our BCA table, and then we do our Henderson-Hasselbalch equation. All right, that's back from chapter midterm 2. All right, BCA table, then Henderson-Hasselbalch. And then what about the point after the equivalence point? What's that? That's excess base, excess hydroxide. Yes, and the calculation will be exactly the same as the previous example. So let's calculate the pH of these things. Oh, I forgot the molarities again. So let's say this is just a generic weak acid. So the Ka is 1 times 10 to the negative 4. So point A, the only thing we have present is HA, no base. So this is just a Ka equals x squared over 0.1 calculation to get your pH. That's point A. That's a chapter 16 pH. Now the new part here is these other points. So if we look at B, we see that now we have HA in our beaker, we're adding a little bit of base, so we're just partially neutralizing it. So it's best to just, again, calculate how many millimoles of each you have to see where you are on your titration curve. So all of these have 5 millimoles of HA, our weak acid, and then now we have varying amounts of our base in all of these. So in the first one, we had 0 millimoles of base. In part B, we actually have 1 millimole of base. In C, we have 5 millimoles of base. And then in the last one, we have 6 millimoles of base. So hopefully you can see just by comparing these numbers, where we are on the titration curve for all of them. In part B, when we react 5 millimoles of acid and 1 millimole of base, where are we on that titration curve? Buffer, yes, this is our buffer, right? So let's see if we can't put the numbers together. So for a buffer, what equation do we use? Henderson-Hasselbalch, yeah? So in our Henderson-Hasselbalch equation, we need to do the BCA table first to figure out how much of the conjugate acid and base are present. What students often will want to do, they'll know, okay, the Henderson-Hasselbalch is pH equals pKa plus log base over acid, but they won't distinguish what base and what acid. They'll just want to put 1 over 5. But 1 millimole is the amount of hydroxide, not of the conjugate base that is in the solution. So if we actually wanted to do Henderson-Hasselbalch on part B, the pH would actually be 4.0, that's what pKa is, if you take the negative log of that Ka value, plus log 1 over 4. Because after this neutralization reaction, how much HA is left? 4 millimoles, while 1 millimole of it is converted to A minus, the conjugate base. Yeah, so that's what the pH would be. Okay, what about point C? What is that? Anything special about this point? That's your equivalence point, yes. So at your equivalence point, you only have NAA present. This is a base. So we're gonna use our KB expression, equal to x squared over concentration of the conjugate base. What's its concentration? Is it 0.1 molarity? No, it's not. You remember, you diluted it. You diluted it. So we have 50 milliliters of the acid, so 0.1 molarity, but now it's in a total volume of 100 milliliters. So the denominator here is going to be 0.5 molarity. So do recognize that a dilution is happening at the same time for point C. All right, that's a chapter 16 question. Okay, and then the last one here, D. What's special about this point? That's a past the equivalence point. Yes, past the equivalence point. So if we can compare these numbers, we started with 5 millimoles of acid. We added 6 millimoles of the strong base. The acid now is the limiting reactant. So what is in excess is 1 millimole of hydroxide. And so now our solution is basic after our equivalence point. So now we just have to divide by the total volume, so 110 milliliters to get hydroxide concentration. All right, so that's basically all titrations. Okay, good. But that's only part of chapter 17 that's being assessed. So let's just keep going. Let's keep going. Okay, I gave a lot of room. The last two concepts with chapter 17 are KSP and KF. These, we're finally doing away with KAs and KBs, where A stands for acid, B stands for base. KSP stands for solubility product. So we're inspecting saturated solutions. I like KSPs because their K expressions are a lot easier because there's never anything on the denominator. Yeah, that's real nice. So let's rank these substances in order of increasing molar solubility. So let's just remind ourselves what a KSP expression is. So let's just do the first one. So if we have silver chloride saturated, we throw a hunk of silver chloride into water. Silver chloride is a strong electrolyte, but it doesn't mean that silver chloride is really soluble in water. What it means is that if any amount of that solid dissolves in water, it's going to break up fully into its ions. So we have silver plus and chloride minus. These are aqueous, right? So in actuality, silver chloride is not very soluble in water, meaning if you throw a huge chunk of it in water, you only make a little bit of the ions, a tiny bit. So you only make a tiny bit of products. So remember back, chapter 15 or 16 or whatever, if you only make a little bit of products in an equilibrium, what is your K value going to be? It's going to be real small. Is K real small? Heck yes, it is. All right. So what is solubility product? This is how you draw out the ice table for our solubility product. So this is the start of a solubility product equation where you take the solid, break it up into its ions with the appropriate coefficients. So silver chloride is easy because it's a 1-to-1 cation-anion ratio, but it does change. So how I go about it is I start with some random amount of the solid. I'm going to just say N amount because that number is never going to go into the K expression because it's a solid. All right, and I have 0 of the other stuff. All right, so I throw the solid in, some of it dissolves. So I'm going to lose X amount of silver chloride, and then I'm going to gain X amount of silver plus and X amount of chloride minus. And so at equilibrium, I'm going to have X amount of the ions and N minus X of silver chloride. So the thing is in the ice table, this N minus X does not go into the K expression, but that's what we're solving for, X. That minus X, this is molar solubility. And that's what we're solving for. So the question is, well, if N minus X isn't into the K expression, how can we calculate it? Well, X shows up on the other side, what does go into our KSP expression. So just like any other K expression, we can come up with the expression to represent the solubility product of silver chloride. It's just going to be the concentration of silver plus at equilibrium times the concentration of chloride minus at equilibrium. See how I'm only including the things with concentrations? I don't include the solid. All right, and just like all ice tables, you just plug in whatever is in the equilibrium line into your K expression. So we can say for silver chloride, KSP is equal to X squared. And I give you the number, it's 1.6 times 10 to the negative 10. And so we just have to figure out what X is. That's it. And so the hardest part, the learning objective, is can you get the KSP expression in terms of X? And it just requires an ice table. But once you do a bunch of them, you'll see that it's not that bad. And they're kind of fun. And I think they're relatively easy. So X in this case is 1.3 times 10 to the negative 5 molarity. What that means is if you have a liter of solution, a liter of water, only 1.5 times 10 to the negative 5 moles of silver chloride will actually go into solution. That's a really small amount, really small amount. Okay, so let's do the next one because this calculation is relatively straightforward once you do one of them. Oftentimes exams don't just ask one, it'll ask multiple, kind of like this, where I'm asking you to rank these substances in terms of molar solubility. I want you to compare the X values. So it's forcing you to calculate 3 of them to make it a little bit harder. So let's do the same thing for lead iodide. So if lead iodide breaks into its ions, we get lead 2+, but we also get iodide. But what's special about iodide here? There's actually 2 of them. And so you do the same thing. You start with N amount of lead iodide, you lose X amount of it, you gain X amount of lead 2+. How much I minus do you gain? Plus 2X amount of it, yes. So when you write out the KSP expression, okay, it's going to be lead 2+ times I minus concentration, but I minus is squared because this is a K expression and there's a 2 coefficient. And then what's the trick with ice tables? It's the equilibrium line always goes into the K expression. So we see that getting K into terms of X, you'll get X times 2X squared. And this reduces down to 4X cubed. And then you set that equal to that KSP value, and you can solve for X. And so you get X in this case is 1.5 times 10 to the negative 3. Okay. So just based upon these two numbers, what is more soluble in water, lead iodide or silver chloride? Which one has a higher molar solubility, meaning more moles of the junk can go into water? The lead iodide, yes, more of lead iodide can go into water because its concentration is to the negative 3, not to the negative 5. All right, and so let's see if we can't do the aluminum hydroxide one without drawing out the ice table. So think about it. This breaks up into ions. You get X amount of silver. How much hydroxide do you get when it splits up? 3X, yes, 3X. But when you put those values into the KSP expression, yeah, that 3X has to be cubed. Yeah. So that's how you get the KSP expression without actually doing the ice table. All right, and that equals KSP. And you can solve for X. So do recognize that like the exponents, they're increasing here. So 3 to the third is 27. X to the fourth equals KSP, whatever that number is. And you solve for X, all right? Okay, good, KSP. Nothing's in the denominator. Okay, I'm gonna keep going. So let's do some applications of KSP. Let's say we have a solution. You all have the key, remember? You have the key, yes. Okay, let's do some applications of KSP. So we have a mixture of lead and silver, and we would like to selectively remove lead ions from solution while keeping the silver ions dissolved. Which counter ion should we use to selectively remove lead 2+ first? So this one is very similar to what we just did, but a little bit harder. So we have a bunch of substances, they have different formulas, but I give you all the KSP values. So I guess one of the important learning objectives here is from the formula, can you get the KSP expression? So you have to understand what that is. We're taking these ionic solids and dissolving them. So hopefully you can get to the KSP expression without writing everything down. KSP for lead carbonate is going to be the concentration of lead 2+ times carbonate. 2-. The KSP expression for silver carbonate is going to be silver plus, but that value is squared because there's 2 of them. You're going to get a coefficient of 2 in that KSP expression, times carbonate, 2-. Okay, lead bromide, we're going to have lead 2+ and bromide squared because there's 2 of those anions present in the balanced chemical equation when that breaks up. Kind of like when you do a net ionic equation. I think that's a good way to do it. When you did net ionic equations and you broke stuff up, that's where you're going to get your KSP expression from. And then finally here, silver plus and bromide minus. Okay, so how does that help me? Okay. We have a solution that already has a set amount of lead and silver present. So we can go ahead and just plug those numbers in to these equations and calculate what is the necessary concentration of the anion that we need to get to obtain the KSP value, essentially. And so when you calculate that, I'm just gonna bring up my key and I'll just show you because I don't feel like writing all these values down. All right. Okay, where is it? We've got a lot to get through. All right, so when you do that, what you're doing here is you're putting these 0.1 concentrations in as the given cation, and what you're going to do is calculate the concentration of anion you need to get these certain KSP values for these substances. So I have all 4 of those here, and so what we see is if given concentrations of 0.1 molarity silver plus and lead 2+, lead carbonate will start to precipitate out at a carbonate concentration of ×10⁻13 carbonate. But silver will start to precipitate out at 6 × 10⁻10. So to me, this means that lead 2+ is going to precipitate first because the carbonate concentration required is lower. But let's, for completeness, look at the next set. If you look at bromide concentrations, lead bromide's not going to precipitate out until the bromide concentration is 0.006 or 0.007. So ×10⁻3. While silver is going to precipitate out when the bromide concentration is ×10⁻12. So that means if you just add a tiny, tiny bit of bromide, that silver plus is going to precipitate out first, as long as the concentration is above ×10⁻12 bromide. That's just a tiny, tiny bit, while the lead's not going to precipitate out until bromide's much higher. So that's the strategy you want to be looking for. But in the question, it's asking you, what do we add to remove lead 2+? So we're looking for the substance that requires the anion to be a lesser concentration for lead 2+. All right. So here is just kind of application of using KSP. In these examples, I give you concentrations, essentially the equilibrium concentrations for one of the substances, and you're solving for the concentration of the other thing, and coming up with a conclusion to see what ion to add to get the resulting observation you want. All right, so there we go. Okay, so there's that. So I think the answer is carbonate. Yes, the first set. All right. So let's talk about some Le Chatelier's principle stuff with solubility. All right, so let's think about what could be an example of the common ion effect on solubility. So we're still talking about KSP. So if we had NaCl solid, all right, and we wrote out its KSP expression, if we add HCl to it, if we add HCl to this system at equilibrium, does Le Chatelier predict anything? The reaction's going to shift which way if we add HCl? Yes, we're adding acid, but technically we're adding, chloride minus. Yeah, so we're adding a product. So the reaction's going to shift to the reactant side. Yeah, so if you were at least in my class and I showed the demo, I had a saturated solution of NaCl. It just looked like water. It looked like water. But it was indeed saturated. They just had filtered it out right before bringing it out. And I added a couple drops of HCl, and we saw the solid crash out of solution because we pushed it over to the reactant side by adding a little bit of chloride. So we see common ion effect. We're adding a common ion and we're reducing the solubility. It's just Le Chatelier's principle. What if I added, sodium nitrate to this equilibrium? What would happen? Nothing? Are you sure? No. Yeah, it's still going to go to the reactant side. Yeah, because this time we're adding sodium. Sodium plus is also a common ion. What if I added potassium nitrate? Nothing would happen. Yeah, because there's no common ion. So adding HCl to NaCl will make it saturated. Adding that will make it make it less soluble. Or how about this one, HBr? What if we added HBr to this? No, but it's an acid. We added HCl and it shifted it. Why can't HBr do it? It's an acid too. It's not the acid part, it's the common ion part that's shifting, like doing the Le Chatelier's principle. So here, HBr has no common ion. Okay. So in general, the common ion effect makes things less soluble, all right? Less soluble in water. Okay, which of these could have be an example of pH dependence of solubility? Select all that apply. So typically, if a solid is going to be more soluble in like acidic or basic conditions, it's typically acidic conditions, right? Acidic conditions will usually make solids more soluble. Okay, but soluble, but there's a caveat, but only if something in the solid can react with acid. That's the caveat. Not all solids will be more soluble in acidic conditions, but if a solid is, it's usually more solid in acidic conditions. And I'll show you why. Acidic conditions, how can you make something more acidic? Add acid. What is acid? H+. Yeah, so this is how I like to think of it. If you look at a solid, if anything in that solid can react with H+, it's going to be more soluble in acidic conditions. So let's think about it. Calcium hydroxide. If we write out the KSP expression for calcium hydroxide, right? Calcium 2+, hydroxide 2-, there's 2 of them, right? Look at the ions. Is there anything in there that H+ can react with? Yes. What? Hydroxide. Yeah. So if H+ eats up that hydroxide, think about Le Chatelier's principle. If you remove hydroxide, remove this, remove a product, which way does the reaction go? Right, to the product side. So remember, calcium hydroxide's a solid. So if it shifts to the products, the solid's going to become more soluble. Yes, so here's an example where affecting the pH, in this case making it more acidic, you're going to remove some of that strong base or that hydroxide, shifting the equilibrium to the ion side, right? So this is why all the crunchy moms on Pinterest, they clean stuff with vinegar and lemon juice. You know what I'm talking about. Okay. So what if we add HCl to ammonium chloride? They are doing something right, those crunchy moms. When they clean with vinegar, they're shifting the KSP, the solubility of solids. So adding HCl to ammonium chloride. So let's write ammonium chloride, okay, the KSP, so NH4 plus chloride minus. What if we added HCl to that? Can HCl, so we're lowering the pH, we're making it more acidic. Is HCl going to make ammonium chloride more soluble? No, for a couple reasons. If we add HCl to this, which way is the reaction actually going to shift? This way, yeah, so it's actually going to become less soluble. Also, H+, it's an acid. It's typically only going to react with what? Bases. Is anything in here a base? No, NH4+ is actually an acid, right? So an acid and an acid, it's not, those don't react with one another, okay? All right, yeah, so A is right, B nothing, or that's actually making it less soluble. Oh, well, actually B, no, there's still a pH dependence, actually, technically. It's just technically not more soluble at lower pHs. So in this one, ammonium chloride is actually less soluble at lower pHs. Yes. So I phrased this incorrectly. I was trying to get you to think. I didn't want to say, oh, add H+. I wanted you to connect it to pH and acidity. Yeah. It is the common ion. Yes, this is the common. B is the common ion effect, but technically it's still pH dependence a little bit. Okay. What if we added HBr to calcium carbonate? So let's think about it. Calcium carbonate, when that dissolves in water, you got calcium 2+ and carbonate 2-. Can HBr, which is H+, react with anything, any of those things? Yes, it can react with calcium? No, yeah, carbonate, because carbonate is a base. So if you add acid to a base, it eats that up, and the reaction shifts to the product side. Calcium carbonate becomes more soluble. Cool. So when you watch TikToks where people are cleaning toilets and they're adding vinegar and baking soda and then cleaning it, you can look at them with a discerning eye and be like, that does nothing, because you're pre-neutralizing it before you clean the toilet. If you want to clean the toilet, like just stick with acid or just stick with base. Don't use both of them, because you're just neutralizing it, right? And then you're just cleaning your toilet with salty water. Okay. Just pick one. All right, let's do the last one. Complex ion formation. This is kind of the hardest one, and it's the most different. Complex ion formation, when we're forming a complex ion, so this first substance is a complex ion, we're always forming it, All right, so these typically have KF values associated with them. These KF values are very, very large. All right, and what this means is when you put aluminum 3+ and hydroxide together at a certain concentration, you will almost predominantly make this soluble complex because KF is really, really large. KF has a different, it has a different form, right? You're forming the soluble complex, all right? So what this means is if you have, if you're forming, if you have, how do I want to say this? I don't want to say this. Okay, if you have like some not very soluble salts, like aluminum phosphate, all right? It's not very soluble. Only a little bit of aluminum goes into solution and a little bit of phosphate goes into solution, only a little bit. So if you remember how we worked with Le Chatelier's principle, if you have a way to remove some of this, one of the ions from solution, if you like remove aluminum 3+, or if you remove phosphate, the reaction shifts to the product side. So KF is another way we can remove aluminum 3+ from this reaction by forming this complex, because KF is a very, very, very large number. So if we have aluminum phosphate, we add hydroxide to it, we will preferentially form this complex, which is soluble, removing aluminum 3+, making the solid more soluble. So it's just another way to remove one of the ions from solution, just like how we removed hydroxide by adding acid when looking at calcium hydroxide. So of these last ones, which ones are examples of complex ion formation affecting solubility? So if we add sodium hydroxide to aluminum 3+ and make a aqueous soluble complex, this will make any aluminum, insoluble aluminum compound more soluble. But if we add sodium hydroxide to aluminum 3+ and form a solid, this does not affect our solubility, all right? Because we're just forming the solid. This is actually just describing KSP, right? There's no complex being formed. Forming an iron cyanide compound. Again, that is a complex. If we looked up the KF for that value, it's going to be really large, and it's going to make any iron 3+ compound really soluble. And then finally here, forming iron carbonate solid. Again, this is just KSP. It doesn't have to do with KF, so that one has no effect on our solubility. Okay. Okay, so let's put all of these things together. Which of these solids will become more soluble in acidic conditions? So let's think about it. Acidic conditions means we're adding what? You're adding what? H+, yeah, proton. So which one of the factors of solubility are we talking about? Common ion effect, pH dependence, or complex ion formation? pH dependence. So understand the rules. If the H+ you're adding reacts with any of the ions in there, typically it will become more soluble. So if you add, can H+ react with F3+ or chloride? No, because Fe3+, iron 3+, that is actually a Lewis acid. If you recall, that's a Lewis acid. And chloride minus, that's just a neutral salt. So what you're looking for is anything that is either a base, a strong base, or a weak base. Weak base meaning like the conjugate of a weak acid, typically. All right, calcium cyanide. Yes, H+ will react with what? The cyanide, because cyanide is a weak base, yes. So yeah, so cyanide is a weak base. Okay, silver fluoride. Yes, because of which one? Fluoride is a weak base. Lead chloride. No. Calcium hydroxide. Yes. What about magnesium hydroxide? Magnesium hydroxide, milk of magnesia. Magnesium hydroxide. I did this demo. I don't think I did it for you guys because it's really messy. Did it for my other class, sorry. Well, milk of magnesia, magnesium hydroxide, will that become more soluble in acidic conditions? Yes, because there's hydroxide there. Okay, all right. Strontium perchlorate. So you're looking at the perchlorate. You have to ask yourself what kind of, basically I'm just asking you, what kind of salt is this? It is, yes, it is salty. Strontium is a neutral cation. What about the anion? It is neutral. Why is perchlorate neutral? Yeah, so perchloric acid is a strong acid, yes. So this one, no, because everything's neutral. Magnesium phosphate. Magnesium phosphate. Yes, that one will become more soluble in acidic conditions. My cat has struvite bladder crystals. That's what struvite is made out of, magnesium phosphate. And so I gave her a high acidic diet to try to dissolve her bladder crystals out because I didn't want to pay for the surgery. And she got kind of better. She got kind of better. Not the whole way, but we still might have to go the surgery route. But yeah, I increased the acidity of her diet and hopefully the crystals dissolve away. How'd I do that? There's like things you can get that just increase the acidity of, you know, like there's like those urine strip tests that you can test for urine acidity, right? Yeah. It's high acid diet, man. Okay. Okay, last one, aluminum hydroxide. Yes, no, yes, good. Okay, because and the last one's here, phosphate is a weak base. It's a weak base because of phosphoric acid is a weak acid. Aluminum hydroxide, again, because of that hydroxide that's there. Okay. Oh, I didn't circle that one. Oh, or that one. I didn't circle a lot of them. Okay. But you have the key. Okay, finally. All right, what question do we want to do? Let's just do the low-hanging fruit. Low-hanging fruit. Entropy. Not quite disorder. I mean, if you call entropy disorder, sometimes you can get in trouble, but it helps us. Understanding number of microstates. As microstates for a sample increases, entropy increases. So if we look at these, if we wanted to order these in increasing entropy, typically we look for things like states of matter. So obviously B, in increasing entropy, it's going to be solid, liquid, gas, because gases have a lot more microstates that those particles can exist in a lot of different places, a lot of different positions, and still have the same energy. While solid, not so much, because the particles are all confined. But if we look at part A, we have a whole bunch of different compounds here. Other than states, what you want to be looking for in terms of entropy, you want to look at things like molar mass of your compound. Also, you want to look at number of bonds, right? All of these samples are in the gas phase, right? So if you have 1 mole of each of those gases, the particles themselves can be in the same number of positions in a certain volume. But we see that hydrogen is the lightest here, so it's actually going to have the lowest entropy. All right, and if we look at these other compounds, we can actually just use molar mass to define all of them, and we'll see that the perchloric acid in the gas phase will have the most entropy. Right? But there's other things that we can consider too. Perchloric acid has much more bonds in them. So remember, all of these are in the gas phase. If you think about like a helium atom just like bouncing around a container, all right, just helium atoms bouncing around. But then if you had the same number of particles of like hydrogen, no, I don't want to do hydrogen. Let's do like nitrogen. Nitrogen bouncing around. So diatomic nitrogen, N2, there's a bond there versus helium, there's no bond. So when a particle bounces around, a container, it's just bouncing around. But nitrogen, when it bounces around, it's also vibrating at the same time. So when you're thinking about microstates, if you can bounce and wiggle at the same time, right? If you can wiggle as well as bounce, then you're going to have more entropy, more microstates present in that sample. Yes. Why? Because there's more microstates. So molar mass typically means you have more electrons. All right, so if we go even to a more like, idea like that, like thinking about the electrons, protons, and neutrons within your sample too. Yeah, good?
Yes.
Okay. So we're, so for when we're just comparing two samples, we're typically going to look at molar mass of the samples, all right? Okay, all right, so we were just looking at the absolute entropies of these substances. I think a better learning objective here is understanding how does entropy change in an actual chemical reaction. So we're looking for entropy changes during some type of change, all right? So we're tracking how is our entropy changing here. So thinking about disorder, thinking about on a particle level, what do these substances look like? And if you think about it in terms of disorder, it'll get you 99% of the way there, and that's fine. So if we think about how much disorder is in silver plus and chloride minus in the aqueous phase, meaning it's dissolved, it's in like a container, right? They're all dissolved in the water. Versus silver chloride solid, is entropy increasing or decreasing? Decreasing, yeah, it's going to decrease here. So it's decreasing, so that means we've actually predicted the sign, delta S is a negative value. What about the next one? We're going from a solid to another solid and a gas. Entropy is definitely increasing, and the reason here is because there's more moles of gas on the product side. What about C? What is the sign of entropy there? Entropy change, sorry. It is decreasing because we're going from 3 moles of gas to 2 moles of gas. Right. What you don't want to do here is think about molar mass. You don't want to think about molar mass here. Why don't we want to think about molar mass? They will all be the same. Yeah, these are all balanced chemical equations. So shouldn't the masses on each side be the same? Yes, they should. Yeah, so don't look at mass. We want to look at things like states of matter, number of particles, number of gas particles, those types of things. All right, okay, true or false? I like these. A combustion reaction is always exothermic and has a positive delta H of a reaction. No, what's the wrong part? It's negative delta H of reaction. Would you have caught that? Would you have caught that? I hope so, yeah. The negative delta H reaction. Because remember, don't be selfish. We love combustion reactions. We love when all that Q flies out, okay? We felt the Q coming off, heat, whatever, energy, because we are the surroundings. So if we absorbed energy, that means the reaction lost energy. That's why delta H is a negative sign for the reaction. The reaction lost energy, we felt it. All right, a decomposition reaction always has a positive delta S of reaction. What is a decomposition reaction? We have something and it becomes 2 things. Yeah, I'm not going to say A, so like B plus B. So delta S is always positive? Yeah, I think so, yeah. Yeah, that's true. All right, the second law of thermodynamics says if delta H of S of a reaction is positive, the reaction is spontaneous. That sounds right, but it's not right. What's the little piece of what piece is wrong? It's not delta S reaction that is positive. What needs to be positive? The universe, yeah, so for any spontaneous reaction, delta S of the universe is positive, where the universe is equal to the reaction and the surroundings. Because we already set up here, there are some reactions that are actually negative in terms of change of entropy. These reactions can still be spontaneous if the change in entropy of the surroundings is very positive. That's how we can still get a positive change in the universe. Yeah, okay, actually that's the next one. If delta S of the reaction is negative, the reaction can still be spontaneous if the delta S of the surroundings is very positive. Yes, that is true. Yes, Here's the idea. The second law of thermo says that universe needs to be positive. So if delta S of the reaction is negative, the only way that can be positive, the universe can be positive, is if the surroundings is a big positive number. Okay, big positive number. If it's a small positive number, it's not going to be, universe won't be positive, but it's a big positive number, then it will. All right. Okay, so that one's true. If delta S of the surroundings is positive, the reaction is very exothermic. Okay, so the equation this is referring to is delta S of the surroundings equals negative delta H of the reaction over temperature. Or negative Q over T, I think. What? It doesn't matter. If delta S of the surroundings is positive, the reaction is very exothermic. Yeah, so if the reaction is exothermic, what is the sign of delta H reaction? Negative. So if you put a negative number into this equation, you get what? Positive. There we go. Yay. Yeah, so that's how we can think about changes in entropy of the surroundings. It's related to any energy or heat that is released or absorbed by the reaction itself. So if you think about it, like when we do the hydrogen balloon demo, right? Energy, heat, it comes off, right? There's a certain delta H of, delta S entropy of the reaction, but the entropy change of the surroundings depends on how much heat the surroundings absorbs. So us, the surroundings, we absorb some of that heat. Our entropy increases because of the exothermic reaction. All right, and that's what E is trying to say. Yeah, so that one is true. When the forward reaction and reverse reactions are both spontaneous, the system is at equilibrium, so delta G equals 0. Yes, yes, this is true. So this is actually referring to a system at equilibrium, so not a delta S universe equals a positive value. So when the entropy change of the universe is positive, these are spontaneous reactions. They move in the forward direction spontaneously, and they are irreversible processes. Irreversible. All right? Irreversible processes. Okay, so let's keep going. All right, so the enthalpy of vaporization of mercury is that. And its entropy of vaporization is that. Calculate the boiling point temperature of mercury in Celsius. So we have mercury. Let's think about how to boil mercury. You're turning a liquid into a gas. So we just said when both the forward and reverse reactions are spontaneous, delta G equals 0. So when mercury boils, both the liquid and gas are present at the same time. We have chemical equilibrium. So if we want to figure out what temperature this happens, we just have to set delta G equal to 0. But we need an equation that helps us that has delta G in it. If you look at your equation sheet, I think like halfway down, we see an equation that says delta G naught equals delta H naught minus T delta S. We are given, oh, there should be a naught there. We are given delta H, we are given delta S for this reaction. If we just set this equal to 0, we can solve for temperature. And so that temperature will tell us, because we've set delta G equal to 0, we're trying to figure out the temperature at which this system is at equilibrium, meaning liquid and gas are present at the same time. That to me sounds like boiling, right? So we just have to plug and chug, but we got to be careful about our units here, because the unit of enthalpy is typically in kilojoules, and the unit of entropy is typically in joules. So you have to convert one of them. It doesn't matter which one, just convert one of them. So setting this up, delta G is equal to 0. I'll convert delta S. So I'll keep delta H in kilojoules per mole minus T, that's what we're solving for. times delta S. So that is equal to 0.0929 joule mole Kelvin. All right, and so you just solve for temperature, and you get that the temperature is equal to something, and hopefully you get a number that makes sense. 636 Kelvin, or 363.1 degrees Celsius. All right, so that's us estimating the boiling point of mercury. So if you know the enthalpy of vaporization for this process, all right, and if you know the enthalpy change of vaporization for this process, you can estimate boiling points or even freezing point temperatures if you know those respective reaction values were there, all right? So I mentioned, get a temperature value that makes sense, because if you did not convert entropy to kilojoules. Oh, this should be kilojoules. Yeah, I changed the value. Yes, if you did not convert entropy to kilojoules, you'll get a number that doesn't make sense, I promise. 59.11 divided by 92.9. You get that T equals 0.636 K. What's that? It's next to 0 Kelvin. Is it possible to achieve 0 Kelvin? That's actually the third law of thermodynamics. It's actually almost impossible to achieve 0 entropy. That actually occurs at 0 Kelvin, which is it's a theoretical temperature. We've never actually achieved that. This number is very, very, very cold. And what is the question asking you? The boiling point temperature. I don't know about you, but to boil something, you typically have to heat it up. So again, think about the number that you're putting into the little box or checking on the thing that it makes sense. To boil something, you're not gonna bring it to 0 Kelvin. Okay. And that's what happens when you don't change the signs or change joule to kilojoules. Okay. Ooh, I like this question. I asked this on my 1250 exam and it did not do very well. Yeah. Okay, without doing any calculations or looking anything up, consider this combustion reaction and choose the true statement. This reaction is spontaneous at high temperatures, low temperatures. It's never spontaneous, it's always spontaneous. How can we figure that out? See, I love this equation. All right, this equation, Gibbs free energy, tells us why stuff happens. A reaction is spontaneous when delta G is what? Negative, right? The reaction's spontaneous. When delta G is positive, a reaction is non-spontaneous, right? I gave you enough information in this question. Okay, depending on the signs of delta H and delta S, we can think about what temperature ranges do we get a negative value of delta G. So let's read through this question again and don't discount any word that I include here. Let's consider this combustion reaction. What did I just tell you? Boom, yes, but numerically, what did I just tell you? Delta H is what value? Negative. Did you just gloss over that? No. No, because you're doing this review with me. Okay. What else? I give you the reaction. So can't we predict the sign of entropy? Yeah. What's the sign of entropy? I don't know. I have to look at it. There's 6 over here and 7 over, yeah, it's positive. Okay, great. All right, so delta G is equal to a negative number minus a positive number. Our goal is for delta G to be negative. So let's think about this. The only thing that we can change is temperature. Temperature can be anywhere from 1 Kelvin to a billion Kelvin. So I like to do this in my mind, all right, where I take the delta S term and I either make it a small value of T, all right? So if we have a negative number and we subtract a tiny positive number, delta G is Still negative, yes. But what if we take a negative delta H value and subtract a really big positive number? It is still negative. So now can we answer the question? This reaction is what, A, B, C, or D? D. It is always spontaneous. All temperatures will make this delta G negative. Yes, great. Let's just do another example. Let's pretend, let's not look at this example. What if we had a combination like a positive delta H minus a positive delta S? At what temperature range will delta G be negative, meaning the reaction is spontaneous? At high, low temperature, all temperatures, no temperatures? High temperatures, yeah, because delta H is already positive. So I like literally in my mind make this term small, meaning low temperatures, or I make it big, high temperatures. So you see when T is big, that T delta S term is big also. So when you do the math, delta G comes out to be negative. Yeah, when T is big. All right, so that's how you do that. Okay. Okay, so consider this reaction. Use the information and calculate delta G, delta H, and delta S at 298 Kelvin. How do we do that? How do we do that with this information given? I give you the reaction, I give you formation values, I give you absolute entropies. To calculate each of these, you just do products minus reactants. Yes. So you just do, where are my products? These two, okay, minus that one. But do make sure that you take into account coefficients. So these numbers you need to multiply by 3, these ones you need to multiply by 2, all right? Products minus reactants, keep into account coefficients, okay? I like to do all of the products and I'll do all of the reactants, sum them up, and then do the subtraction. All right, I'm not gonna do those. Okay, but that's review. That's like 1210, products minus reactants. Now the new part is let's calculate the K, the equilibrium constant for this reaction, right? Because this is an equilibrium. So what thermodynamic piece of information is related to K? Delta G, yeah, it's on your equation sheet. There's not many places K, actually no, K comes up in a lot of places, but not a lot of them are related to thermodynamic pieces of information, and in this case it is delta G. So delta G equals negative RT ln K. So we already calculated delta G. I'm just going to tell you what it is. Here you go, 30 more minutes. 30 more minutes. Jeez. All right, so we just plug in the numbers. I got, when we did this, the products minus reactants, you would have gotten delta G equals positive 128.93 kilojoules. Okay, so when you plug this number into this equation, can we keep it in kilojoules? Why not? Yeah, so R, do you remember what the unit of R is? 8.314 joule per mole Kelvin. So can we keep delta G in kilojoules? No, we can't. So this has to be positive 128.93 times 10 to the 3 joules equals RTK. ln K, sorry, equals. All right, so then we have temperature 298 and then ln K. And then you just solve for K, great. And so since this delta G value was calculated from a table value, these table values are at standard conditions, meaning at 298 Kelvin. That's why we have 298 Kelvin in this equation, because it changes a little bit for the next question. I told you it's at standard conditions, which implies 298 Kelvin. Here in C, I ask you calculate the equilibrium constant for this reaction. not at standard conditions, instead on the surface of Venus, which is this temperature. This temperature, all right? So what a lot of students will just try to do is shove this temperature in here and then solve for K again. But we can't do that. Temperature, remember these table values, they're at standard conditions, meaning they're measured at 298 Kelvin. Delta G values change with temperature. But we're going to make an approximation that says that delta H's and delta S's of reactions do not change with temperature. So we actually have to calculate a new value of delta G at non-standard conditions. And so to do that, we're actually going to go back to this equation, delta H minus T delta S. All right, we have a new temperature. We're going to plug that in. We actually already know delta H, delta S. We're assuming those values don't change with temperature. And we'll get a new delta G value at this new temperature. So now I actually have to tell you what delta H and delta S are of the reaction when we did products minus reactants. All right. So delta H is positive 120 kilojoules, and then delta S is negative 27.84 joule Kelvin. All right, and so we plug in those numbers, 120.55. I'm going to change delta H to joules, so it matches entropy. New temperature, minus 748 Kelvin times delta S, so negative 27.84 joule Kelvin. And this will give us our new Gibbs free energy value. Yeah. The what equation? I don't. Oh, it's on the supplemental. I'd have to check it. Did you try it? I need to check it real quick to see if you do get the same answer. So I'm not gonna say it right now. Okay, all right. So this is how, yeah. So this equation looks very similar to the 2-point Arrhenius equation, but it's actually a little bit different because the Arrhenius equation one has activation energy. Yes. Yes. Okay. All right, so let's get our new delta G value at 748 Kelvin, and we get a number like 1.41 times 10 to the 5 joules. So this is a different number than what we had at standard conditions. So the strategy here is you need to get delta G at a different temperature using delta G equals delta H minus T delta S. And now with that new delta G value, we can set that equal to RT ln K, where T is now equal to 748 Kelvin, and we're solving for this K. And so we'll get a different answer. We'll get a different answer. So K is a new value. It is 1.34 times 10 to the negative 10. Or you have that on the key. All right, so that's the strategy for that question. All right, so, okay. Okay, so let's just do one more in chapter 19. Let's do 18, but let's just start at C. So let's consider the KSP for chromium hydroxide. So let's just remind ourselves what that looks like. All right, so we have chromium hydroxide, it's a solid, it goes to that. You get chromium 3+ plus 3 hydroxides, aqueous. Right, we did those before, KSP, right? Okay. So that's for a saturated solution of chromium hydroxide. So let's just skip to C. What would the value of delta G be for a saturated solution of chromium hydroxide at equilibrium? At equilibrium. 0, yes, it is 0. So if you look at B and C, See how B has a knot in it and C does not have a knot in it? That's not a mistake. Delta G knot, this is at standard conditions. So this value is related to negative RT ln K. We are given K, KSP in this case. So you could calculate delta G knot. It's related to KSP. Delta G is related to systems not at standard conditions. So if we have a system at equilibrium, right, concentrations are going to be a little bit different than the concentrations you would measure at equilibrium, or sorry, at standard conditions. So delta G is equal to 0. When it's at equilibrium, we can think, oh, the amount of solid isn't changing. The amount of dissolved stuff isn't changing. So the forward reaction is not spontaneous. The reverse reaction is not spontaneous. Well, I guess both of them are spontaneous at the same time, at the same rate. So delta G is 0. There's no driving force for the forward or reverse reaction to happen. So this, we can relate this idea to Le Chatelier's principle. Remember how, like, you know, when we talked about Le Chatelier's principle, I said, okay, we have this at equilibrium. I add chromium 3+. Which way does the equilibrium shift? If I add this, yeah, it goes that way. Why? Yeah, but that's not thermodynamically why. So your classmate said, oh, we added more products, the reaction goes backwards. That's not a thermodynamic reason why the reaction shifts. So if the reaction goes in reverse, what would the sign of delta G be at that moment if I added chromium 3+? If the reverse reaction is spontaneous, delta G should be what sign? Positive, yes, because when the forward reaction is spontaneous, delta G is negative. So if delta G is positive, that means that the reverse reaction is spontaneous. So let's prove it. Let's prove it. When we add, if we have too much product present, delta G is positive, which predicts a reaction shift to the reactant side. So you know our fun, quick and dirty way we did Le Chatelier's principle, nice and fun. Okay, it's actually delta G at non-equilibrium conditions. All right, so let's say we have a solution that is this concentration chromium with this pH. Will it produce a precipitate? So, is this at equilibrium? No. So we need to calculate, so we're not calculating K, we're actually calculating Q. Yeah, so the equation that we're using here is actually delta G equals delta G naught minus RT ln Q. Right, so we just need to calculate Q. But remember, Q has the same expression as KSP. So Q in this case is going to be concentration of chromium 3+ times concentration of hydroxide minus cubed. Right, we have all the information we need to calculate Q. Chromium, we have that. But what about hydroxide concentration? I give you pH, so that means POH is 7, which means hydroxide concentration is 1 times 10 to the negative 7. So you just plug all those numbers in and get a Q value. So chromium is 0.1 molarity, 1 times 10 to the negative 7 molarity cubed. Q is equal to, I don't know, 1 times 10 to the negative 22. Okay, so let's just go back to chapter 17 for a moment. If we compare Q to K, in this case KSP, and I tell you it's times 10 to the negative 31, just looking at those two numbers, you should be able to predict if a precipitate forms or not. Will a precipitate form or not? Yes or no? Yes, yes. And the reason is Q is larger than K. Okay, so remember, K generically is products over reactants. So if K or Q is big, you have too much what? Products. K is big, right? K equals products over reactants. So if Q, which is also products over reactants, is bigger than K, you have too much products. So that means the reaction is going to shift to the reactant side. What is in the reactant side? The solid. Yeah, so when you have too much concentration of this stuff, it's going to push to the solid side. So that's us doing Q versus KSP. That's chapter 17 stuff. But let's prove it numerically with a delta G calculation. So let me just give you what delta G actually is. It is 170 kilojoules per mole for this reaction. You just plug in the KSP value. So let's actually calculate the delta G value at these conditions. So if I'm telling you that the solid forms, that means the reverse reaction is spontaneous. I'm going to just predict that delta G is a positive number before we calculate it, but we're actually going to calculate it here also. All right, so let's plug in those numbers. So we're using this equation, delta G equals delta G naught, which I just gave you, that we got from KSP. So 170 times 10 to the 3 joule per mole minus R, so 8.314, times temperature, so 298, times ln Q. We already got Q, it's 1 times 10 to the negative 22. All right, and so when you do that operation, you get negative 125.5 times 10 to the 3 joules. And so what you get is delta G is equal to positive 44.5 times 10 to the 3 joules per mole. And so yes, we do in fact get a positive value of delta G, meaning that the reverse reaction is spontaneous at these conditions, meaning that a solid precipitate forms because we have too much ions on the product side. So we're going to throw some of it, we're going to throw some on the ground, all right, to get it out of the KSP expression, throw some into the solid phase, so then we can achieve the value of KSP in this case, which is 6.3 times 10 to the negative 31. Right, so that this last question kind of summarizes everything in chapters, the end of 17, Le Chatelier's principle, and its relationship to Gibbs free energy, which I like. I like that. Okay. Okay, so that's all of 19. Isn't the equation plus RT? Oh yeah, sorry, it is plus. Yeah, sorry, that's plus. It's correct in my key. Yeah. Right here. Delta G equals negative RT ln K. In this case, KSP. I gave you KSP. Yeah. Yeah, I just kind of skipped that step. All right, so we have like 20 minutes left. What do you want to go over in electrochem? Yeah. The what? 21. Yeah. Okay, yeah, so actually let me clarify something. I got this question so many times this weekend. Okay, so what's the equation they give on the, oh, they don't even give this equation on the equation sheet. Okay, cool. All right, so the equation that I teach my students is that the standard cell potential, right, if you're given a bunch of standard cell potential half reactions, you're given a bunch of those, right? Your standard cell potential is the reduction standard cell potential of your cathode minus the reduction half reaction standard reduction potential of your anode. So what kind of reactions happening at your cathode? Reduction, and then at your anode, oxidation. Just memorize that, red cat and ox, just memorize it, okay? At reduction is at your cathode, oxidation is at your anode. So once you've identified what is being oxidized, what is being reduced, whoops, you know what reaction's at your cathode, what is your anode. So you just look for the numbers on this table and you just do one number minus the other number written as is. These are reduction half reactions, okay? So you just take one reduction value minus the other reduction value, granted that you correctly identify what is your cathode, what is your anode. So the question I got over this weekend was, well, okay, I understand that these are all half reactions, right, in the reduction form. All of these things are being reduced. I know that, these are the cathode. Well, what if zinc is my anode, all right? If zinc is my anode, that means zinc is being oxidized. That means this reaction isn't happening, it's the reverse reaction that's happening. So oftentimes students will flip this reaction, and then they will flip this reduction potential value. They'll flip this reduction potential value and then put it into this equation, okay? So that's fine, and I understand why you want to do it. You want to do it because you want to treat it like Hess's law, right? You have a reduction reaction, it's giving off electrons, you have an oxidation, or the other way. You have a reduction reaction that's consuming electrons, you have an oxidation reaction that's giving off electrons, right? You flip one of them, so you flip the sign of the cell potential. But if you do that, then you have to add your reduction and your oxidation cell potentials. You have to add them. But if you use this form where it's cat minus anode, both of those values have to be in the reduction form, meaning written as is. You can't flip the sign and do minus at the same time. I think I answered that email like 6 times this weekend. I'm like, you can't do both. You gotta pick one. This negative sign does the flipping for you. Yes. If it was an electrolytic cell, we typically are not calculating negative values, so that doesn't apply here. All right, so do keep that in mind. Both of these values are the reduction form, and that will help us answer 21, and then we might have to be done here. All right, so cell 1, I give you the cell potential. We just need to figure out what is being oxidized, what's being reduced. So we got to track it. So we got to get our oxidation numbers. What's the trick with oxidation numbers? It's basically charge. If you can think charge, that's basically oxidation number. So what is the oxidation number of lead solid? 0, yeah, because the charge of lead is 0. What about H plus? Plus, plus 1. Lead 2 plus, plus 2. H2, 0. So with those numbers, you can figure out what is being oxidized and reduced. Lead 2 plus, its oxidation number is going up, so it is being oxidized. H plus, its oxidation number is going down, so it is being reduced. Cool. Okay. So I give you the cell potential. So it looks like here we're trying to figure out what are the reduction potentials for these for the cathode and anode. So there's a little piece of information that you should know already. You should already know the reduction potential of one of these half reactions already. Which one is that? Hydrogen. Yes, what is the cell potential of a standard hydrogen electrode? 0, yes. So it's 0, hydrogen is 0. But what is hydrogen? Is it at the cathode or the anode? Where do I put that 0? Does it go here or does it go there? Goes where? It's being reduced. So since this is SHE, this is 0, so our 0 is going right there. All right, that's our hydrogen value. So this is equal to 0.13 volts. Okay, so that means the reduction potential of lead, which is our anode, is whatever that math turns out to be. What is it? Negative 0.13. Oh no, sorry. So this number, how do I want to say this? The reduction potential of lead is equal to negative 0.13 volts. I'm going to quickly just scroll up to that table and see if we're right. Are we right? Yeah, thank goodness. Okay. It's the reduction potential. Even though lead is being oxidized here, because we did cat minus anode, the reduction potential comes out. Okay, we're going to keep this piece of information in our back pocket, because what is used in the second cell potential, or second cell? Lead again, yes. So lead again, but is lead the anode? No, we gotta, now that we have that piece of information, we just need to put it in the appropriate spot. So we do the same exact thing again, get our oxidation numbers. 0 is X, lead 2 plus 2, plus 2, 0. So now lead is actually being reduced, and X, our mystery substance, is being oxidized. So we set up the same equation. Our cell potential is equal to cat minus anode. So in this case, we have different numbers. 0.74 equals, where am I putting lead? This negative 0.13 number, cat or anode? Cathode, yes, because it is going from plus 2 to 0. It's being reduced. So we're putting the negative 0.13 in the cathode place, minus the reduction potential of the anode. In this case, it's X. And you just solve for it, all right? And whatever that answer is. I think it is the reduction potential of the anode of X is equal to negative 0.87 volts. Yay. Okay. Good. So this is good practice in, how you do this calculation. Again, don't flip the reaction and flip the oxidation sign and do subtraction. You can't do both. Just pick one or the other. I don't know how your instructors taught it, but I just did cathode minus anode. That's how I taught it. But they both are in the reduction form. Both are in reduction form. Okay. All right, I'll do one more question. Let's do 23. What? Solve what? No, that's what we just solved for, right? The reduction potential of X. What equation is this? This is the equation where X is being reduced. Okay, well, let's just do 22 real quick. Okay, let's put it all together. All right, for a spontaneous reaction, what is the sign of delta G? Negative, yes. When we have a spontaneous electrochemical cell, a voltaic cell, what's the sign of E cell? Positive, yes. A redox reaction with a positive cell potential has what kind of K value? It has a very large K value, yes, yes. That it's gonna wanna go towards products. A redox reaction with a negative cell potential, so not very spontaneous, has what kind of K value? Small, because if you have a lot of reactants to start with, your cell isn't spontaneous, it doesn't go forward, your reaction's gonna stay on the reactant side. So K, big K, is gonna stay small. All right, so we'll just talk through 23. All right, what is the effect of our cell potential for the following changes of this reaction? So this is kind of a qualitative idea of our Nernst equation. The measured cell potential that you measure is equal to the standard cell potential minus some numbers. I don't quite remember what the equation is. Yeah, that's right. Over N log Q, where Q is the same as K in this case. So we could look at our Q expression. Q is concentration of zinc 2+, pressure of H2, zinc solid's not in the equation, H+ concentration squared. So we will only measure a cell potential related to the table value if Q is equal to 1. When we're at standard conditions, Q is equal to 1 because the concentration and pressures of everything is 1, so Q is 1. So what we measure is what we get from the table values. But the thing is well, what if we change Q in such a way, we can alter the actual measured cell potential that we measured away from the table values when we do cathode minus anode. So with the naught, so E cell naught, that is our cathode minus anode calculation. We won't always measure that value. We won't always measure that value, right? We can change it depending on the concentrations. So let's say we increase the pressure of H2. How will E cell change? We're not really calculating anything here. We can just look at Q and think about how it changes. So if we increase H2, how does Q change? It increases, yes. So if Q increases, how does log Q change? It also increases. So E cell minus a big number, our measured cell potential is actually going down, yes. So here's the strategy. I see, okay, H pressure of hydrogen goes up, Q goes up, like negative, or I guess log Q goes up. So that means E cell, without the naught, what we actually measure, goes down, because this is a large number. The stuff you're subtracting is a large number. Okay. What if zinc nitrate is added to the anode half cell? So it looks like, what are we adding? We're adding zinc 2+. So what's changing? How does Q change? Goes up. Log Q also goes up. So how does the cell potential, the measured cell potential, change? Goes down, yes, because log Q again is a big number. Okay. What if we add HCl to the cathode half reaction? So this time we're adding H+. How does Q change? It decreases. So if Q decreases, log Q, it actually becomes, if Q is less than 1, so if Q is less than 1, log Q is actually a negative number. Yeah. Yeah, and so if log Q is a negative number, cell potential actually goes up, right? Because if you subtract a negative number, cell potential becomes more positive. Okay, so what if we increase the pH of the cell? What are we essentially doing? If we're increasing the pH, becomes more basic. So that means H+ concentration goes down. Yeah, so Q, right? Because you might be like, oh, if you increase pH, you're adding hydroxide. Hydroxide's not in the Q equation, but hydroxide, when we talk about pH, yes, it means hydroxide, but it also means H+. So H+ is going down, Q is actually increasing, log Q is also increasing, so our measured cell potential will actually go down. Right? So the general idea here is, if you shift the reaction, if you think Le Chatelier's principle, if you have more, if this is a spontaneous reaction, all right, if it has a spontaneous cell potential, all right, it's positive. It's going to become more positive if you add reactants. If you change it in some way where you add reactants, because when you do that, Q becomes smaller. If you add products, the idea is we want the reaction to spontaneously go from reactants to products. If you already have a lot of products there, that push isn't going to happen as much. So if you add products, Q increases, your measured cell potential actually decreases. All right, so that's basically the trend there. All right, so I'm gonna end there. Good luck. Thanks. Okay. If you're in my class on, we're gonna probably just continue the packet at 8 a.m.